video for class number 22. I'm a little behind, so I'm trying to catch up. So if we have a combined types of loadings, different loading modes, we want to get the von Mises for the alternating and the mid-range, and then use them together in one of our failure criterion, whether it be Goodman, Gerber, ASME, or Soderberg. So one thing we can do is we could use these equations 655 and 656, where we have von Mises, and you can see where we have the fatigue stress concentration applied to the bending and to the axial and the torsion. And one thing that stands out here is this 0.85. Well, the instructions here we should have in 0.5, when we get the endurance limit, when we calculate that with the modifying factors, we want to use specifically KB and KC, do it for bending, right? And so where that gets adjusted in the alternating stress for axial, we divide by 0.85, right? So where we would have applied 0.85 for the loading of KC in the endurance lift, if it was completely axial and fatigue, we divide by it. So that's going to be essentially doing the same thing. But you notice that we don't have that 0.59 times divided by the torsional, right? So that doesn't do the equivalent thing, and you kind of ask why. That's because this 3 right in here functions as the same thing. That 3, if you recall, 1 over the square root of 3 is 0.577. So that's like the thing that makes it into a shear strength, right? We made shear endurance strength by taking a 0.59, but here instead we're taking the stress and turning it into, taking that shear and converting it back into normal stress with our 3. I hope that makes kind of sense. But anyway, they're connected to each other. So, and then over here in the mid-range, because it's not a fatigue thing, we're not going to compare it to fatigue. We're only going to compare it to either the yield or the ultimate, depending on which of the criterions we use up above. We don't need to do that adjustment. Now, these equations are way longer than they need to be, because really, honestly, I don't know what kind of scenario we would come up with where we would have all 6 of these types of stresses. Most of the time, what we'll see for the scenarios is we'll have like the bending perhaps will be alternating, but then all the other stresses will either be 0 or will be constant, so they don't have an alternating component. And then maybe we'll have in the mid-range, let's say the torque is going to be constant, so then we don't have these, right? So we quickly can make these equations much shorter than they look here. I'm not going to answer this question down here. I did it in class, but this was just a demonstration of that sigma A prime plus sigma m prime added together is actually going to be a larger number than if you just found out what the maximum sigma prime was going to be, right? If you just found the total von Mises. So, but anyway, let's go into this example, put this in through its paces. And so we have problems 380 and 647 from Shigley, at least the 10th edition and earlier. And we have a load that's only 325 pounds. I mean, not only, but it's 325 pounds only in the Y direction here. And we want to try to determine the location of the critical stress. And we want to find the factor of safety in modified Goodman. And if that's less than 1, estimate the number of cycles for this. Okay, so let me see. Alt-tab into the camera. Boom. No, didn't do it. Alt-tab. Oh, I see. I gotta go to that. Boom. Okay. That's a nice. What a lovely tablecloth we have. I didn't pick it up. So I'm going to break my own rules here, and I'm not going to do the FBD, but you really should almost every time. Here's an exception where I'm not gonna. So let me close this thing down. All right, so maybe the first thing I'm going to do is I'm going to find out some material properties, and I'll get the yield. And this was for 1018 cold drawn. We find we get 54 KSI and an ultimate strength of 64 KSI. The moment, let's see, well, I'm going to draw this in here. I believe we were showing that this is a 325 pound load, and it is repeatedly loaded. So repeatedly loaded, that's the key word right here. That means like it's an on-off loading, right? So as a loading versus time, it goes load off, load off, load off, right? So this maximum is at 325 pounds right there, and it goes between, cycles between that on and off. So the moment, the maximum moment is going to be when this thing occurs right here, but it's going to be in both. Or do careful. Let's see. It's only going to be about the z-axis, right? So there's no moment about the y-axis. If there was, we need to find both of those and find out when they were in the maximum here. But we have a moment about the z-axis that's taking place, and I'm drawing the equivalent moment, right? Not the reaction moment, because this is not a free body diagram, right? We're also going to get an equivalent torque right here. That's going to be happening, right? So this thing is going to cause a twisting motion about the x-axis. So that's also about the x-axis. So like it's not too terribly difficult to get these, but so that's one of the reasons why we can go ahead and do this without a free body diagram. You just observe this force, and the distance perpendicular to it is 6 plus 2. So we get 2,600 inch-pounds. And the moment about x, wow, that was really great. X, should just read it, right? Equal torque. 325, and the moment arm is going to be this distance at 5 inches. But once again, I'll repeat, so much of your life can be made easier by embracing the free body diagram and not taking shortcuts. But in this case, don't be like me, kids. Okay, so I'm going to need stress, so I'm going to get the I. I don't have axial, so I don't need to get the moment. I don't need to get the area, but I do need to get this, which is going to be, in this case, it's just 1 inch diameter, they say. So, fourthed. Not that it matters, it's 1, but it's okay. 0.04909. Should be pretty familiar because we've done a lot of stuff that was 1 inch in diameter. And then J was just 2 times I, or 0.09817 inches fourthed. So we can get a maximum and nominal with our MC over I, or the 2600 times the C, 0.5, and R, 0.04909. So we get, and I divide it by 1,000, just because it's close to being K. You know, it's 26,000, so I'm going to, let's just shorten it down. It's by my dividing it by 1,000 is right there, represented by that K. Right? And now we got the torsion, TR over J, 1625 and 0.5, and now R, 0.09817. So we get a lovely 8.276 KSI. And the minimum nominal is 0, and the minimum nominal for the torsion, or the torsional shear, is 0, right? So we're flopping back and forth between those. We were given that the stress concentrations at the hypothetical fillet that are right there is 1.5 for bending, and we don't care about the axial, and 2.1 for torsion. So we need to modify those, And it didn't quite tell us. Did it tell us what the notch was? Did I say anywhere where the what the fillet radius was? Yeah, oh yeah, 0.1. Right there, 0.1. Right. So we can look up this, I don't know, I started writing 1. We can write up this Q, look this thing up in like figure 620 and get 0.753. We could do the same thing for the shear one in figure 621, and it's 0.803. So our capital KF is 1 plus Q times our KT minus 1, right? And so that's 0.753 times our, in this case, this is 1.5 minus 1. And we're left with 1.377. It's the stress concentration in fatigue based on bending. And KFS 1 plus QS KTS minus 1. And we don't necessarily have to go through all those numbers, but I did anyway, right? 2.1 is what we were given, minus 1. And we get 1.883. Great. That was, we could have done that actually later, because I'm going to get the nominal. Am I going to do that? No. Oh, we want to get the nominal amplitude. Oh, mid-range and yes. Okay. So right now we have maximum. So what we really want to get is the mid-range, and well, we'll see here in a second. We'll actually see, because of this special case of being on-off loading, that the mid-range and the alternating, or the amplitude, are equal to each other, because we have max plus min, right, divided by 2. So that's simply going to be 26.48 plus 0 divided by 2, which gives us 13.24 KSI. But if you think about it, the alternating, I guess I was going to do it there, is the max minus the min. But the min is still 0, right? So you're still getting 26.48 minus 0 divided by 2. So no need to do that. So they're equal to each other. We could anticipate the same thing is going to be true with the alternating shear right here. And we know that it's just going to be 1/2 of the max. So just 8.276 divided by 2. And remember, that's just because it's the special case of on-off loading. So that comes out to 4.138 KSI. So that also is going to apply to our von Mises. We also know that these are going to be the same thing, but let me write out the alternating one first. So I'll write out the equation as it applies. I'm going to leave out the axial one because it's not in there, right? So let's see, I put these brackets in the right way. I think I messed up these brackets. They're like unnecessary brackets. Let me double check back over into here. And you can see, yeah, those brackets were only in there because of the, no, I guess so. Okay, yeah, they're covering in the fact that we have parentheses inside, right? So, got a bracket here in the KF times sigma A. We're dropping the nominal thing off of there. Squared. I don't know why we have that in there. It does seem unnecessary, those parentheses. Yeah, they are. Plus 3 times KFS tau A squared. 1/2, right? So just plug in the numbers in. I guess now I can put the things in there because I'm going to put numbers. I like to have the parentheses around numbers. I don't know if you noticed that. 1.377, and then the 13.24, and then square that plus 3 times our 1.883 times our 4.138 squared, and take the square root. And so we're going to say that that's going to be 22.68 KSI, notably, which is also going to be equal to the mid-range, right? Because nothing in there is any different in this case of the on-off loading. We want to get the endurance strength. Let's just say that we did with all of our KAs and KBs. There's KA, KB, KC, KD, KE, and then the elusive lowercase kf, which has been left out of the 11th edition for good reason. Didn't need it. But anyway, I decided, I think this is cold drawn, and these are values that are going to correspond to what you would get if you were to apply the modifying factors from the 10th edition and earlier, with the 11th edition being slightly different. So we get 0.8969. For KB, it's not rotating, so we needed an equivalent diameter before we go back and put it into the other thing that gets the KB. And anyway, that comes out to a boring 0.977. I say boring because it's practically, in all intents and purposes, it's 1. It's not that much. It's very small. KC, we're going to treat it like bending, and then all the others, I think. And then we take 1/2 of the ultimate, which I said was 64. So what we end up with is 28.06 KSI. So we can now proceed to get our safety factor. So we start out with Langer, and that's going to be LANG. I take the yield strength and I divide by the alternating plus the mid-range. Right? And so the yield strength was 54. The alternating and the mid-range are both 22.68. And what we're left with is 1.19. So it's pretty close, but remember, this is conservative because if we, we're really just looking about the first cycle yielding. And if we were to just go ahead and take this stress right here, using these maximums and apply the stress concentration, we would get a smaller number than this plus that. But whatever. And I don't know if that's always the case. I think mathematically, I think I was able to show that one time. I was able to pick numbers where they actually did come out to be the same. But for the most part, this is going to be a conservative thing. So the next one I'm going to do is Soderberg. No. I was only asked to do Goodman. All right, so we'll do Goodman. And I might be able to fit everything on this one page. And that's going to be 1 over, remember, alternating divided by endurance plus mid-range divided by ultimate. Right? That's an apples to apples, right? These are both fatigue types of things, fatigue stress and fatigue strength. We have mid-range, which is a constant stress, and here's an ultimate, which is a constant strength. So we 1 over our, I guess you don't necessarily need to put in values, but you kind of see here where this comes from. 0.6 and then plus 22.68 divided by our 64. And what we're left with is a 0.86, which is less than 1, therefore finite, maybe, or not infinite. So we want to get the reversible stress. And that's an equation where we take the alternating and divide it by 1 minus the mid-range divided by ultimate. And what that's effectively doing is drawing a line through our, I don't have graph paper here, but I can draw the thing out here on a separate sheet of paper here. Remember, what we've done here is on a graph of alternating versus mid-range, we've taken our endurance strength and our ultimate strength, drawn a line, kind of like that. And what we found, okay, so in this case, we're like just below here, just below there. So we have like right here, this should be like a 45-degree line because they're equal to each other for this special case. That's the load line. We can see we're outside of this. So what we're effectively going to do is draw a line that starts at ultimate and goes through here and connects with the alternating thing to give us an equivalently reversed stress. And that equivalently reversed stress is going to allow us to estimate what the life is using this very, very flawed method. Right? This is not a reliable method because we're treating it like it's, as they like to say, deterministic when it's actually a stochastic. And if I could pretend like I know what that means, we're, instead of just being in one particular number, we should be looking at a cloud of numbers because it's, talking about ranges of things and stuff, that kind of thing. So anyway, this comes out to 35.13. So if we now use that F, right, first, that F we look up from a figure. I didn't write down what the figure number was, but we look up that F. I have Shigley here, so I'll go down to, I don't know if I need to do this, but that's okay. I'm doing it anyway. So we get the F from this figure right there. And you note that we're 64 KSI, which is less than 70. And it says right below that just use 0.9 if you're less than 70. And we're going to do that by, what we're going to do with that is to put that into this equation and this equation. And then we're going to be able to put those, that A and that B, into this equation and find the number of cycles. So laziness says that I'm going to be putting that A, if I find that A, I get 118.2, and B is a negative 0.1041, right? Then I can find my number of cycles is that rev, as I just showed, 35.13 divided by my A, raised to 1 over negative 0.1041. And what I'm left with is 120,000 cycles. And I've only used 2 sig figs in there because anything more than that sort of, in my opinion, implies more certainty than we actually exist. So there you go. That was the first problem. I'll try to do the second problem here and try to get you done with it quickly. Thank you.